Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to you all in massive open online course under NPTEL on plates and shells. In my introductory video, I have given different topics that have to be covered on the course plates and shell. You have seen that the course is distinctly divided into two parts. One is about the plate and the second part will be about the shell. First, I will cover the plate and then I will take up the chapters on shells. In plates, I will cover 7 modules and in the shells, I will cover 5 modules. After completion of each module, you will receive the assignment based on the lectures given in the modules. And there will be a final examination also in this course, and I encourage all of you to appear at the exam, and you can test whether you have learned it the subject or not. Also, I will have satisfaction if you learn the subject and able to apply in practical problems. Now, today it is my first lecture on this subject plates and shells, and first I will start the chapters on plates, and this is the module 1 and first lecture of the module 1. So, in this lecture I will give you the introductory topics on the theory of plates and how the topics can be utilized to formulate the problems in plates that will be discussed. So, the plate that I want to cover in this subject will be introduced gradually, and first the introduction to theory of plate that I will cover today will consist of 5 sections that you are seeing here. So, first section will deal with the classification of plate theories, second section will deal with the fundamentals of plane elasticity, third section deflection, slope and curvature of the plate, fourth section displacement strain relations, and then stress strain relations. So, all the topics that I have listed here are actually the background topic, you can call it, and the relations theory that will be discussed in this class will be later used in formulation of the problems in plates. Okay. Now, let us see what is the plate. You have seen that in my introductory video, I emphasized that plate is a thin structural element and it is used in various fields of engineering, civil, mechanical, aerospace, marine. Everywhere you get the structural component with a thin element, and this behaves as a plate. So, plate is a thin structural element whose thickness is very small compared to other dimensions. So, if I see the major dimensions of any structure, that is length, breadth and thickness, then you will see that thickness is very small compared to length and breadth. So, therefore, this type of structures gives advantage in reduction of weight, and also it has high rigidity in flexure as well as in axial deformations. So, it is bounded by 2 flat surfaces. So, the surfaces of the plate are flat before the application of the load. After application of the load, the bending will take place, but before the application of the plate initially it is bounded by two flat surfaces and with straight or curved edges. Plate may have straight edges or it may have curved edges. The distance between two flat surface is known as thickness. So, in a plate where the surfaces are two top and bottom surface that you are seeing here are parallel, in everywhere this thickness is constant, but there may be situation where thickness varies along the plate dimension. Okay. Then a term that we will be encountering in theories of plate, that is known as middle surface, which is a plane parallel to the plate surfaces that bisects the thickness of the plate. So, this is the middle surface that I labeled here, you can see, and this is the thickness at this point. Okay. And plates are found in different shapes. Most common application of the plate is rectangular plate, and circular plates are also found in applications, elliptical shape, in any other shape, triangular also frequently encountered or encountered in some cases that we have to analyze it. So, different shapes are common. Okay. Now, first let us discuss what are the different theories based on which we will proceed to formulate the problems on plate. Three theories are developed for studying the plate. First theory is a thin plate with small deflection. Second theory is thin plate with large deflection, and third theory is a thick plate theory. Okay. Now, in the first theory, the deflection of the plate is small in comparison to the thickness, and generally this deflection is assumed to be less than 1/5 of the thickness. So, in this type of plate, the bending moments, twisting moment and shearing forces are produced in response to the external load. Then the second theory says that the plate is thin, but the deflection may be large. So, this theory is known as thin plate with large deflection. So, what happens here? Let us see. In this case, deflections are not small as compared to the plate thickness. So, that means where we define the limit here in the thin plate with small deflection, this limit may be exceeded here with thin plate with large deflection. So, therefore, due to large deflection, the geometric nonlinearity will be produced, and as a result of large deflection, the in plane stresses are also produced in the plate in addition to bending moment and twisting moment. So, in plane stresses that are produced will alter the nature of the problem, and the governing differential equations of equilibrium and solution techniques also will be different compared to the thin plate with small deflection. Then third theory is thick plate theory. In this theory, the thickness of the plate is larger, and it is generally assumed that it is greater than 1/10 of its longer dimension, and therefore, due to its thickness is significant, and therefore, the shear deformation contributes to the deflection. So, thick plate theory considers the shear deformation in the deflection of the plate, whereas this thin plate with small deflection, the shear deformation may be neglected, is insignificant. Similarly, in the thin plate with large deflection, we need to consider the geometric nonlinearity in the governing differential equation of equilibrium. Okay. So, in our course, we will mainly focus on the thin plate with small deflection, and we will develop different theories and to solve the bending and buckling of the plate using the classical method as well as some numerical and approximate technique. Okay. So, to study the plate, one requires to know fundamentals of elasticity. So, because we consider the plate as a continuum where the properties, physical properties of the system, that is you can call its this weight, self weight, or you can call moment of inertia, etc., are distributed in the space domain. So, therefore, the all properties including its stiffness, flexural rigidity or axial rigidity, whatever you consider in the problem, are generally function of space variable. Now, in general, any structural element has three principal dimensions, and first we should know the stress system or the background of the stress and strain that is produced in a structural element in general with a three dimensional flavor. Then from this condition or this formulation we can simplify it to the plate, because in plate the thickness is considered to be negligible, and therefore, the two dimensional elasticity formulation will be considered mainly. Now, let us consider a small rectangular parallelopipe as shown here. So, you are seeing a parallelopipe whose length along x direction, along x axis is dx, along y axis is dy, and along z axis is dz. Okay. So, volume of this small element is dx, dy, dz. Now, here I have shown the stresses on the faces of the parallelopipe. So, on the 6 faces the stresses are there, but I have shown here the stresses in 4 faces, and other faces can be similarly constructed or written. Okay. Now, in general, in any elastic body there is normal stress as well as shear stress. Now, consider this face. So, this face is parallel to yz plane. So, in this face the x axis is normal, or the axis normal to this face is parallel to x axis, Cartesian axis x y z. So, normal stress is denoted by sigma x, and there are two shear stresses that are acting tangential to the plane. So, that stresses are denoted as tau x y, tau x z. One interesting thing you are seeing here, that normal stresses are denoted by sigma accompanied by a single subscript, whereas the shear stresses, that is the tangential stress, that are denoted by 2 subscript with a symbol tau. Okay. Now, there is some meaning of this subscripts, why it is given to, why 2 subscripts are associated with the stresses. The first subscript denotes the direction of normal to the face. So, here in this face you can see the direction of the normal is x. So, therefore, first subscript x is associated here. Second subscript denotes the direction in which the stress acts. So, here you can see the stress acts along the z direction. So, therefore, second subscript is given as z. Similarly, here you can see tau x y, x denotes the normal to the face and y denotes the direction in which the stress acts. In this phase, we see that normal stresses is sigma y, and the shear stresses are tau y z and tau y x. Okay. First subscript you can see here is y, that clearly indicates that y is the normal to this face. So, the first subscript is written as y, and second subscript z denotes the direction in which the stress acts. Similarly, here also you can see that the tau y x, because y is the normal direction of normal and x is the direction in which the stress acts. Okay. There are different sign convention possible, but generally on the positive faces stresses acting along the positive direction of axis are considered positive, while on the negative phase the stresses acting along the negative direction of the axis are considered positive. Now, in engineering application customarily the tensile stress is considered positive, but there is no hard and fast rule. One can take the sign convention in other way also. You can see one thing, that in this phase we have denoted the normal stress as sigma x. The two shear stresses are tau xz and tau xy. On the opposite phase, if you see, the normal stress is written as sigma x plus and shear stresses are written as tau xy plus and tau xz plus. Why plus sign is given? The meaning of this is that on the opposite phases the stress will change. So, the increment or decrement whatever takes place will be denoted by another quantity. This quantity can be found from Taylor series expansion, and if you consider the first term only, then the total stress here that I written only sigma plus will be equal to sigma plus del sigma x divided by del x into dx. So, similarly other stress with increment can be written. Now, here you can see that I consider the partial derivative, because the variables, that is stresses or the whatever you consider in this 3 dimensional problem are functions of x, y, z. So, therefore, partial derivatives have to be brought into picture. So, normal stresses are denoted generally by sigma throughout in our discussion, and it is also denoted or symbolized with a single subscript, and shear stresses will be generally denoted by tau, symbol tau, and it will be accompanied by 2 subscripts. If you see the resultant stress in any phase, say consider this phase, here the stresses are normal stresses are sigma x and the shear stresses are tau xz and tau xy. Now, if I assign the unit vectors along x, y, z axis as I, j and k, which is customary I, j, k. I, j, k are unit vectors, that means magnitude of I, j, k are 1 and its directions are, direction of I is along the x direction, direction of j is along the y direction and direction of k is along the z direction. So, vectorially I can write sigma equal to sigma x I plus tau x y j plus tau x z k, where I, j, k are the unit vectors along the respective Cartesian axis. The magnitude of the stress on this phase can be found the resultant of this quantity, and this is nothing but root over sigma x square plus tau x y square plus tau x z square. So, the stresses can be written or expressed in vector form also in any phase or any plane also. Now, 3D state of stress at any point on elastic body can be represented by 9 components of second order tensor with pertinent matrix. These stresses are considered to be second order tensor, and the matrix that I write will consist of 9 components in general. So, what are the components? Let us see. One is sigma x normal stress, tau x y is the shear stress, tau x z is the shear stress, which are acting on the plane that we have seen. The plane is this plane, that is parallel to y z plane. Okay. Next, tau y x, sigma y, tau y z, then tau z x, tau z y and sigma z. This shear stress is symbolized by tau. Okay. Now, you can see the normal stresses are sigma x, sigma y, sigma z, and the shear stresses are tau x y, tau x z, tau y x, tau y z, tau zx, tau zy. Now, it has been seen that due to reciprocal law in structural mechanics that has been developed by Maxwell and later improved by Betti, and then these stresses are found to be symmetrical. So, shear stresses are found to be symmetrical, that means tau x y is equal to tau y x, tau z x equal to tau x z and tau z y equal to tau y z. Now, symmetry is due to reciprocal law of shearing stresses, and symmetry can also be established from moment equilibrium condition. So, if the symmetry is not there, the cubic element or any element will not be maintaining the moment equilibrium, that means rotation is bound to take place. Okay. So, moment equilibrium is not maintained if the shear stresses are not symmetrical. Then for any body forces are present in the system, and body force is due to self weight, that is one primary body force. Then other type of body forces may be your magnetic force, or if the body is in motion, then inertia force. So, in presence of body forces, the equilibrium of this 3D elastic body can be established by 3 differential equations. Actually, there are 6 equations of equilibrium. 3 equations that I have written here as 1 point A, 1 point B, 1 point C are derived from force equilibrium in x, y and z direction. Other 3 equations of equilibrium are from moment equilibrium, and that we can see that symmetry of the shearing stress, that is nothing but the result of moment equilibrium. So, tau x y equal to tau y x, tau y z equal to tau z y, or tau z x equal to tau x z. These are actually moment equilibrium equation actually. It is obtained from moment equilibrium equation, and other 3 equations that you are seeing here, 1 point A, 1 point B, 1 point C are obtained from the equilibrium of forces that I have shown you this a parallel pipe, and I have shown the stresses on each faces. Here the stress will be written fully including the incremental quantity, that is sigma x plus del sigma x by dx del x into dx, like that. So, similarly here the incremental quantity on the other face for sigma y can be written as sigma y plus del sigma y by del y into dy. So, all the incremental quantity can be written, and then if I sum up the forces in each direction, that is x, y, z direction, I will arrive at these 3 equilibrium equation. So, first equation is obtained by considering the equilibrium of forces in the x direction. So, you can see the equilibrium of forces, first one del sigma x by del x plus del tau x y by del y plus del tau x z by del z plus f x. F x is the body force that is distributed in the element, okay, or in the body. So, all the forces or quantities sigma x, tau x y, tau x z, even this f x are functions of x y z. Okay. So, in the second equation, which is resulted from the equilibrium condition in y direction, that is written as del tau x y by del x plus del sigma y by del y plus del tau y z by del z plus f y equal to 0. So, this is second equilibrium condition. Third equilibrium condition is del tau z x by del x. This is the partial derivative of tau z x with respect to x plus del tau y z by del y, that means partial derivative of tau y z with respect to y plus del sigma z by del z plus f z. F z is the body force, component of the body force in the z direction. So, these are component of the body forces in the x y z direction. So, three equations of equilibrium that I have written here are from force equilibrium condition. Okay. Other three equations of equilibrium are this, that is from moment equilibrium condition. Okay. Now, the three dimensional stresses are simplified in case of plates. So, the plates are actually is a two dimensional case, and we need to ignore some stresses, because here the thickness is small compared to other dimensions. So, all stress components on the surface parallel to x y plane, that here say this x y, this is the x direction and this is y direction. So, x y plane is the plane of the plate. So, here you can see that tau z x, tau x z, tau y z, tau z y and sigma z. Sigma z is the normal stress on the plate, that is plane of the plate that is lying in the x y plane. So, if I consider a normal stress here, sigma z is 0 in case of plate problem, and the shearing stresses that are produced here tau z x. If you see tau z x, z is the direction of normal. So, and x is the direction in which it acts. So, this is neglected, and similarly its the symmetry part, that is tau x z are also neglected, tau y z and tau z y are also neglected. So, these quantities are treated as 0. So, this is very important assumption or condition in case of plane problem, that is plane elasticity problem. So, matrix representation becomes simpler. In case of 3D elements, we require 9 components of stress to write the matrix. Now, here we will write the matrix in 2 by 2 form. The elements are sigma x, sigma y, these are normal elements, diagonal elements you can see here, and tau x y, tau y x are the off diagonal elements, and these are the shear stress. So, due to symmetry, tau x y can be taken as tau y x, and this is normal stresses sigma x and sigma y. So, in a plate problem, the stress analysis will consist of evaluation of normal stresses as well as shear stress tau x y. The stresses that are written in the Cartesian coordinate system x y z can also be represented if the frame of reference is rotated. So, here say for example, the frame of reference x y z, original frame of reference is denoted by x y z, x is small letter, y is also small letter, z is small letter. So, if this frame is rotated about the z axis, then let us see what will be the component of stresses. Okay. So, the frame is rotated counterclockwise with an angle theta from the original configuration. So, now new axis becomes capital X, capital Y is the new axis, capital X and capital Y is the new axis. There are other directions, say 1 and 2 I have marked here, and this direction is denoted as alpha, measured from the original x axis, and obviously this other direction that is written as a number 2 is orthogonal to the direction 1. So, x and capital Y are new frame of reference. So, our intention will be to find the stresses that is transformed in the new coordinate system. Okay. So, if you see the stresses in a element in the original frame of reference, this is the stress sigma x and this is normal stress sigma x and this is shear stress tau x y. Similarly, on the other face, that is normal stress is sigma y and the shear stress is tau x y. So, here also you can see the normal stress and shear stress are also existing. Okay. I want to find the stress component in the new frame of reference. So, new frame of reference is capital X and capital Y, whereas the new x axis is inclined at an angle of theta with the original x axis. The angle of rotation is anti-clockwise. So, with that given information, I can transform the stresses in the new direction capital X and capital Y. So, how to do this? There is systematic procedure. If I can find the transformation matrix is given as cos theta sin theta minus sin theta cos theta. So, it can be easily verified that transformation matrix consists of based on that the angular rotation, that is the angle in which the frame is rotated, can be established by writing the equations of equilibrium of all forces along the inclined plane. So, that is also another way, that not using the matrix method or matrix product that I will show, one can also find it transformation by establishing the equilibrium of the forces along the inclined faces. So, both the methods if you apply, the result will be same. So, here the transformation matrix that I show is 2 by 2, that is cos theta sin theta minus sin theta cos theta. Using this transformation matrix, the transform stress can be written as the product of 3 matrices. So, what are the 3 matrices? First matrix is transformation matrix T, second matrix is sigma, that is the original stress matrix, and third matrix is transpose of this transformation matrix. This superscript T denotes the transpose of this matrix. So, superscript T can be written as cos theta minus sin theta, then here it will be your sin theta cos theta. So, transpose can be done for this matrix and the last matrix is transpose of transformation matrix. So, if you perform the triple product, the T matrix is shown here and sigma matrix is shown earlier. Sigma matrix is shown here, sigma x, tau x y, tau y x and sigma y. So, if you perform the matrix product, triple product, then you will get the transformed quantity. So, transformed quantities are sigma x, that is with reference to new axis capital X, sigma x equal to, this is original stress, that is stress with reference to original axis. So, sigma small x cos square theta plus sigma y sin square theta plus 2 tau x y sin theta cos theta. Similarly, this second transform stress, that is sigma capital Y is equal to sigma x sin square theta plus sigma y cos square theta minus 2 tau x y sin theta cos theta, and tau x y is minus sigma x minus sigma y sin theta cos theta plus tau x y into cos square theta minus sin square theta. So, the stresses in the two directions are available now. Two direction normal stresses and shear stresses are available, that is sigma x, sigma y and tau x y in the new frame of reference are now available with the help of transformation. Now, in this figure I have shown other two direction 1 and 2 with an intention that there may be particular direction in which there is no shear stress. So, we are interested to find that direction. So, in order to find that direction, we equate this quantity to be 0. So, equating this equation 7, that is tau capital X y equal to minus sigma x minus sigma y sin theta cos theta plus tau x y cos square theta minus sin square theta to be 0, we get the tan 2 theta is equal to 2 tau x y divided by sigma x minus sigma y. So, that is the value of particular angle in which there will be no shear stress. So, that direction is known as principal directions, and it gives the direction of principal plane on which only the normal stresses act and there is no shear stress in the principal plane. Once we find the theta, other direction can be found as theta plus pi by 2. Principal stresses are obtained, and the principal stresses are the extreme stresses. So, once you find the value of theta, that means tan theta is found here, and then we can utilize the value of theta in this expression to find the principal stresses. So, in that cases, for particular value of tan 2 theta that I have shown here, 2 tau x y divided by sigma x minus sigma y will result 0 shear stress. So, tau capital X y is 0 for that particular orientation. So, only these two normal stresses will exist, that is sigma x and sigma y, and these will give you the principal stresses. One will be maximum and other will be minimum. Now, here question arises that the cos square theta sin square theta is there, but the actual result or expression is obtained in terms of this tan 2 theta. So, we can convert this tan 2 theta as sin 2 theta and cos 2 theta simply by using the Pythagoras theorem. So, sin 2 theta is found to be 2 tau x y divided by root over sigma x minus sigma y whole square plus 4 tau x y square. Similarly, cos 2 theta can be found as sigma x minus sigma y divided by root over sigma x minus sigma y whole square plus 4 tau x y square. Now, in earlier equation, the cos square theta sin square theta can be written using the trigonometrical identity. Say you know that 2 cos square theta is equal to 1 plus cos 2 theta and 2 sin square theta equal to 1 minus cos 2 theta, and 2 sin theta cos theta is equal to sin 2 theta. So, if I use this trigonometrical identity and utilizing this expression of sin 2 theta cos 2 theta, we ultimately arrive at the principal stresses. So, principal stresses are found as sigma x plus sigma y divided by 2 plus minus half root over sigma x minus sigma y whole square plus 4 tau x y square. One thing you can note here that two values are obtained from this equation. One value will give the maximum stress and another value will be given as a minimum stress. So, maximum stress is called as major principal stress and minimum stress is called as minor principal stress. The maximum shear stress, the absolute value of maximum shear stress is found as tau max equal to half mod, this is absolute value, difference of sigma 1 minus sigma 2. Okay. So, one interesting thing you can see here, that is sigma x cos square theta plus sigma y sin square theta plus 2 tau x y sin theta cos theta, and another expression you can see here that sigma y equal to sigma x sin square theta plus sigma y cos square theta minus 2 tau x y sin theta cos theta. If we add these two quantities, then a very interesting relationship is obtained, sigma x plus sigma y equal to sigma, this is capital X, sigma capital X plus sigma capital Y, that is with reference to transformed axis, is equal to sum of the normal stresses with reference to original axis. So, this quantity, that is sum of the two normal stresses, that is the sum of the diagonal elements in the stress matrix, is known as first stress invariance I 1. So, the conclusion is that the I 1 does not change. I 1 is what? The summation of the diagonal elements of the stress matrix, that is the sum of the normal stresses, does not change with the rotation of the axis, and it remains invariance of the reference frame. So, therefore, this quantity is known as stress invariance, and it is known as first stress invariance. So, there is other stress invariance. It can be proved that sigma capital X into sigma capital Y minus tau square capital X y equal to sigma x sigma y minus tau square x y. So, you can note here, this is with reference to the transformed axis capital X and capital Y, and these quantities are with reference to original axis, that is small x and small y, and again these quantities are equal, which signifies that it is this quantity is also invariant of the rotation of the axis. So, this quantity is known as second stress invariance, and it is denoted by I 2. Mathematically, it can be written with the determinant I 2 equal to sigma x tau x y tau y x sigma y. So, if I expand this determinant, I will get this quantity. Okay. Now, let us discuss about the deflection, slope and curvature of the plate. Now, in a slightly bent plate, we neglect deformation due to in-plane forces, because we are considering the theory of thin plate with small deflection, and as a result the deflection and slope both are small quantities. The slope in x direction is given as theta x equal to del w by del x, theta y is equal to del w by del y. Let us find the slope in any arbitrary direction a dashed. A dashed is this direction, and this direction we call it n direction. This is our x direction, this is y direction, and length of this side is dx, length of this side is dy. So, the difference between the deflection in a and a dashed is due to slope in x and y direction both. So, let the difference be dw. You can see here the deflected line is shown in the x direction. So, the difference of deflection you can note here, it is nothing but this w plus del w by del x into dx minus w. So, we can write now the difference of deflection at a point which is due to contribution of slope due to both direction. Here I have shown the deflected line only in x direction, but there is also deflected line in the y direction. So, considering the slope in both the direction, we can write the change in deflection dw is nothing but del w by del x into dx plus del w by del y into dy. So, this equation is written. We are interested to find the slope along this direction, that is n direction. Okay. So, slope in n direction, that is a dash direction, is written as del w by del n equal to del w by del x into dx by dn plus del w by del y into dy by dn. So, this follows the chain rule of calculus. Okay. From figure, now if you consider this figure where this is dx, this is dy, and this hypotenuse you can symbolize it as dn. I have symbolized it as dn. This angle is alpha, So, from this triangle it is obvious that dx by dn is cos alpha and dy by dn is sin alpha. So, now this equation that we have got using the rule of calculus, then we can write now del w by del n equal to del w by del x, this quantity remains as it is, and here we have written cos alpha. Similarly, here del w by del y and sin alpha is written for dy by dn. So, we clearly distinguish this function or this expression, and we can now assign an operator, that is operator which relates to the normal direction. So, the here actually the equation number is 13, actually it is the slope along the normal direction at the edges or at the boundary. So, here this operator del by del n can be written or like that, del by del n cos alpha del by del x plus sin alpha del by del y. So, this operator we will use in later. Now, let us find the direction of maximum slope in a slightly bent plate. In any arbitrary direction, say n direction, the slope is given by del w by del n equal to cos alpha del w by del x plus sin alpha del w by del y. For maximum value of slope, we differentiate this quantity with respect to alpha and say this alpha is alpha 1. So, we find the derivative of this del w by del n at alpha equal to alpha 1. So, this is written as minus sin alpha 1 into del w by del x plus cos alpha 1 into del w by del y, and it is equated to 0 for finding the maximum value. After simplification, you will get tan alpha 1 equal to del w by del y divided by del w by del x. So, this is the condition for getting the maximum slope. For finding the 0 slope, let alpha is equal to alpha 2 and then equating the original expression of the slope. This is the expression of the slope in any arbitrary direction. We equate this expression to 0. So, therefore, if this direction is alpha 2, then we can find tan alpha 2 equal to minus del w by del x divided by del w by del y. So, at a particular angle, say alpha equal to alpha 2, the slope value is 0. One interesting thing you can note here, that tan alpha 1 is equal to del w by del y by del w by del x, and tan alpha 2 is minus del w by del x into del w by del y. So, if I multiply tan alpha 1 by tan alpha 2, the quantity will be minus 1. So, from this expression we can conclude that direction of maximum and minimum slope in a slightly bent plate is mutually perpendicular. So, this is a important conclusion in our slightly or small deflection theory of the plate. Okay. Now, let us see what is the curvature. Curvature of the bent surface is numerically equal to the rate of change of slope. If the curvature is positive, the plate is sagging, therefore, we have the curvature in x direction written as 1 by r x minus del by del x into del w by del x, which is equal to minus del square w by del x square. Similarly, curvature in y direction is written as 1 by r y equal to minus del by del y into del w by del y equal to minus del square w by del y square. We are interested to find the curvature along n direction, that is any arbitrary direction a dash. So, again we find the derivative of this quantity del w by del n with respect to n. So, this will give the curvature along the direction a dash. Now, using the earlier relation that we have found the operator del by del n, and this operator is written here minus cos alpha del by del x plus sin alpha del by del y, and this slope we have also found out del w by del n, which is written as cos alpha del w by del x plus sin alpha del w by del y. So, if I carry out the term by term multiplication, then I will get 1 by r n equal to minus cos square alpha del square w by del x square plus 2 sin alpha cos alpha del square w by del x del y plus sin square alpha del square w by del y square. Let us introduce a term which is known as twisting curvature. So, twisting curvature is nothing but 1 by r x y equal to del square w by del x del y. So, 1 by r n equal to cos square alpha 1 by r x minus 2 sin alpha cos alpha 1 by r x y plus sin square alpha 1 by r y. To find the curvature in any direction perpendicular to a dashed line. So, what we got actually earlier, this is our a dashed line. So, we have found the curvature along the a dashed line. Now, if I want to find the curvature along another direction which is normal to a dashed line, say this direction is n direction and this direction is t direction. So, curvature in this direction is written as 1 by r t, and to find this curvature we simply substitute alpha by alpha plus pi by 2. So, substituting this alpha equal to alpha plus pi by 2 in this expression 19, we will get 1 by r t, that is curvature in another orthogonal direction is sin square alpha into 1 by r x plus, because this cos alpha when it is substituted as cos alpha plus pi by 2, it will be minus cos alpha. So, therefore, this middle term will be positive. So, plus 2 sin alpha cos alpha 1 by r x y plus cos square alpha 1 by r y. One interesting thing you can note here, if I add these two quantities, that is 19 and 20, you can see this term will get cancelled, the middle term will get cancelled, and 1 by r n plus 1 by r t will be cos square alpha plus sin square alpha into 1 by r x plus cos square alpha plus sin square alpha into 1 by r y. So, after adding this we get 1 by r n plus 1 by r t equal to cos square alpha plus sin square alpha 1 by r x plus cos square alpha plus sin square alpha 1 by r y. So, this quantity is 1. So, therefore, we can write 1 by r x plus 1 by r y. So, this expression also gives a very important conclusion. The sum of the curvature in any two orthogonal directions in a slightly bent plate is constant. Okay. Twist curvature with reference to n and t direction can be obtained as 1 by r n t cos alpha del by del x plus sin alpha del by del y into minus sin alpha del w by del x plus cos alpha del w by del y, and after simplification the final expression becomes 1 by r n t into 1 by r y minus 1 by r x sin 2 alpha by 2 plus 1 by r x y cos 2 alpha. This you can see, this is the operator, okay, and this is operator d by d n, and this is del w by del t. Okay. So, we now get the twist curvature del square w by del t del n. So, term by term multiplication again results this quantity, and using the trigonometrical identity that 2 cos square alpha equal to 1 plus cos 2 alpha and 2 sin square alpha equal to 1 minus cos 2 alpha and 2 cos alpha sin alpha equal to sin 2 alpha. Ultimately, we get the twisting curvature with reference to n and t direction as this expression, the equation number 21. So, it is nothing but 1 by r y minus 1 by r x bracket that sin 2 alpha by 2 plus 1 by r x y cos 2 alpha. Okay. Let us now come to the strain displacement relationship. So, a plate here whose length is dx and width is dy is deformed to this shape. Original this plate was ABCD, now it is deformed to A dashed, B dashed, C dashed and D dashed. So, the displacement of the point B, you can see two components of displacement we are writing here, u plus del u by del x into dx, this is the x component, and y component is v plus del b by del x into dx. Okay. Similarly, if I show the displacement of the element the corner point C, the two components, one is along x direction, it is written as u plus del u by del y into dy, and another component that is in the vertical direction, it is v plus del b by del y into dy. The component of displacement in x and y direction of the point A dash is u and v. So, strain in x direction can be written as the change in length in x direction u plus del u by del x into dx minus u divided by dx, we will get this del u by del x as the normal strain in the x direction. So, this is the normal strain. Strain in y direction, that is also normal strain, is similarly obtained as epsilon y equal to del v by del y. Let us obtain the shear strain. So, shear strain is calculated as the sum of the angle this phi 2 and phi 1. So, if you see this deformation, I have separated this here in a triangle, you can see the vertical displacement, that is the change of vertical displacement is del v by del x into dx in a length of dx. So, tan phi 2 will be del v by del x into dx by dx, and since the deformation is or rotation is small. So, therefore, we can take tan phi 2 equal to phi 2. So, phi 2 we have written del v by del x into dx divided by dx. Similarly, if I see here the component of displacement, the horizontal component of displacement of the point C, the change of displacement, that is del u by del y into dy in a length of dy. So, tan phi 1 if I calculate. So, tan phi 1 is equal to phi 1 because the phi 1 is small, can be written as del u by del y into dy divided by dy. So, shear strain is nothing but del v by del x plus del u by del y. Now, in a strain, when we in a 3-dimensional or 2-dimensional object, when we calculate the strain, it should obey some condition, that is known as strain compatibility condition. So, before going to mathematical equation, first let us see what is the physical meaning of compatibility conditions. Compatibility condition, actually it is needing a continuous single valued displacement. So, in a structure the displacement should be continuous and single valued. If this is not obtained by analysis, then we find that our assumption is wrong, or this numerical technique or whatever solution method we adopt is wrong. So, strain must satisfy the compatibility condition. Now, here you can see lamina or plate is taken and it is discretized or divided into number of elements. So, consider only 4 elements here, 1, 2, 3, 4, I have marked it, and these elements are shown in undeformed states. So, you can see the elements fit together, there is no discontinuity and there is the displacements are single valued, that is a corner you can get the single displacement. Okay. Now, if the plate is strained or under the action of load and it is getting deformed, then in the deformed consideration, if the deformation is carefully done or plate is carefully strained, then in the deformed position we will also see that elements fits together taking consideration of the neighboring elements. That means, there is no separation from the neighboring elements. So, this type of deformation gives a continuous single valued displacement function. Now, if the compatibility is lost or continuity of the deflection is lost, you will find that the individually elements are displaced without any concern for the neighboring elements. So, there is a formation of gap and voids in the domain or in the continuum. So, that type of situation gives this does not obey the compatibility condition of the displacement. So, therefore, deformed consideration discontinuous displacement is seen here, and in the analysis we should always see that continuous single valued displacement is obtained, which is satisfied by the strain compatibility equation. So, strain compatibility equation can be obtained very easily from the strain expression that we have derived, the normal strain as well as shear strain, and compatibility conditions for strain is given as del square epsilon x divided by del y square plus del square epsilon y by del x square equal to del square gamma x y by del x del y. Gamma x y is the shear strain. Okay. So, in a mechanics problem, when you solve for plate or any other structure, adopting any method, numerical techniques or analytical techniques or finite element method, finite difference method, we should see that equilibrium conditions as well as compatibility condition must be satisfied. Okay. Stress strain relationship for the plate: in normal direction, if stress is epsilon x, then it is given by 1 by E into sigma x minus mu into sigma y, where E is the modulus of elasticity and mu is the Poisson ratio of the material. Similarly, in other direction, that is y direction, epsilon y is given by 1 by E into sigma y minus mu into sigma x, and then shear strain gamma x y is equal to tau x y divided by G, where G is the shear modulus and it is given by E divided by 2 into 1 plus mu. You may clearly note that G is dependent on E and mu. So, there are only two independent material constants, that is modulus of elasticity and Poisson ratio. Now, if I solve the equation 26 and 27, because these are actually simultaneous equation with two unknowns. Say if I consider sigma x and sigma y are the unknown in this equation, whereas epsilon x and epsilon y are known, for example, then solving 26 and 27, we can write sigma x equal to E divided by 1 minus mu square into epsilon x plus mu into epsilon y, and sigma y equal to E divided by 1 minus mu square into epsilon y plus mu into epsilon x. So, these are the expression for stresses, normal stresses sigma x and sigma y, which will be concerned in our plate problem, because the other stresses sigma z is treated as 0 or insignificant in case of the analysis of plate, thin plate, and shear stress tau x y is now given as G into gamma x y. So, G is the shear modulus of the material G, which is obtained from E and mu. So, let us summarize today's lecture, which is the introductory lecture, that is the introduction to the plate theory and the background materials required for formulating the plate problem I have discussed in this lecture. So, in this lecture discussion was done on the classification of plate theories and fundamental relations of plane elasticity required to study the plate theories. Deflection, slope and curvature of the plate of slightly bent plate have been derived, and conditions for maximum minimum slope, characteristics of principal curvature of slightly bent plate were derived. Displacement strain relations and compatibility conditions were given. stress strain relation for plane elasticity and material constants are introduced. So, with this background material, we will now proceed to formulate different problems in plate and to solve it to find the deflection and stress resultants. Thank you very much.